All right, so here's the basic radar interpretation we're going to talk about. This is a plot. All these little blue dots indicate where all the weather radar, the National Weather Service or DoD, Department of Defense weather radars are across the United States. There also are now a lot more FAA radar sites. The FAA, this is an older graphic here showing the one down here, but there's actually a lot more of those that are popping up now. So this is a typical picture of what the radar looks like. In fact, this is my radar before we tore down the old one. Inside this white ball is a 28-foot satellite dish. This is what it would look like if there was no dome over it. This is the interior of what it would look like. And so the gist of it here, there's several different radars that we like to talk about. The Weather Service radar is the one all the way to the right. There's an acronym, Weather Surveillance Radar, 1988 Doppler. 88 was just the year. That's the radar that we got. And of course, since it was 1988, but in actuality it was deployed in the 90s, it takes a little while for things to get out. So high resolution, large and expensive, that's what the Weather Service has. The picture in the middle is what typically the media has. And in fact, both TV stations here in town, they have a 5 centimeter wavelength radar. And these are examples of what the towers look like. The tower size itself may be as big as this, or it may be slightly smaller, like a 12-foot dish versus a 28-foot dish. But the big difference here, this bottom point here, is it suffers from attenuation. Because of the 5 centimeter, when it hits the rain, it gets attenuated, and it's very difficult for those types of radars to see through the rain itself and see what's going on behind it. So that's the problem with typical TV station radars. Now, on the other hand, on the left side here, if you get the portable Doppler radars, the storm chasers that you see on TV, they'll have a truck with this a radar literally in the back, and they'll tilt it, aim it, and scanning it back and forth across a tornado. Very short wavelength, so they've got to be in the clear slot of a storm facing the tornado. This is certainly not something that they're going to get any useful data if they're stuck in the middle of a rainstorm. So it's very high resolution, but it's very limited range. I mean, you got to be on top of the storm to see what you're looking at. So these are the three types of weather radars that are out there that we all use from the weather service perspective. And this kind of interesting little slide here, just talking about how the whole process works. It's interesting. One radar pulse lasts 0.000000157 seconds. So not very long. Basically it sends out a signal, it bounces off the cloud, it comes back, and using that time that it does, it calculates math to determine how heavy the rain is, where it's located, and what the wind speeds are as it's doing all that. So you can see that for every hour, if you added up all these pulses, these 0.00015 second stuff, it adds up to 7 seconds out of a 60-minute period. We're actually sending out a radar beam. So think about that compared to your cell phone, compared to your microwave dinner that you're making for 2 minutes. I mean, our radar literally is turned on for 7 seconds, or sending out a signal, I should say, 7 seconds in 1 hour. The rest of the time, it's listening. So that's just the way the radar works. Because a lot of people worry about the radars and am I going to get fried by it and stuff like that. And it's certainly not an issue for radars. And now this is a weather radar. Same thing. The same basic principle applies for the FAA radars that detect where the airplanes are and stuff like that as well.
You said 5 minutes or so. Is that because it's moving its beam around?
Yeah, this is an example here of the various scans. There's each of these different sections on here. You can see 0.5, 0.9, 1.3, 1.8. These are different elevation scans. The radar's going up, scanning at each individual level. So to scan from the 0.5 up to the 19.5 takes approximately 4 to 5 minutes.
What about going around the circle?
Yeah, that's what it's doing. It's doing this 0.5, staying at that one elevation, going around twice, taking its measurements. Then it tilts up to the 0.9, does the same thing, tilts up again. So this is your typical severe weather scan, VCP 212, where it's got a lot of slices, anything from 0.5 to 19.5. And so it automatically changes between 9 to 14 elevations, tilts in 4 to 5 minutes to give you that 3D view of the storms out there. So yeah, it's not just pointed one direction like the portable Doppler radars in the back of a truck. This thing here is spinning around measuring it as it goes around. Then it tilts itself up, spins around, tilts up again. And that's why it takes 4 to 5 minutes to do all that. So typically what you see on TV, the internet, smartphones, is just the lowest elevation angle of the storms. And so this is a single radar site indicating where the rain is. So the color schemes on these things are all usually fairly similar. The light rain is indicated by the green, orange, heavier rain, red being the heaviest rain. There's a lot of limitations. We talked about this in the previous class as well. The further away from the radar beam you go, the bottom of the radar beam goes higher and higher in the sky. So 100 miles out, we're looking at almost 12,000 feet up in the air. So that's why, like from the perspective of tornadoes and stuff like that, I mean, 40 miles is really, to me, a fairly good limit of usefulness for seeing most tornadoes. And even that, you're not going to, not all tornadoes go 3,000 feet in the air to see it. And so this is kind of an interesting feature here. The exact same storm, one's closer in, one's further out. You're going to be missing events the further away they go. This is just a good example to show that we may be totally missing the tornado on the ground over here, whereas we had a better shot of that feature being seen closer in. So this is another example of the 3D feature of all the different scans, the half-degree elevation all the way up to 19.5. 19.5 is as high as it goes. The reason being, the usefulness of anything higher than that, you can see, would literally only be within 20 miles of the radar. So, if you're within 20 miles of the radar, we can see up to 50,000 feet, which is probably a pretty good height in the sky as it is. Most storms don't go much higher than that in this part of the country. But there is obviously a zone close into the radar where we're not seeing much, we're not seeing much, we're seeing nothing, I should say, close into the radar. And so they call that the cone of silence. So like in this picture here, there could be storms lined up all the way from this storm here in the central left side of the picture. There could be another one right here in the middle, but the cone radar beam is going to be totally oblivious, missing it as the storm's passing through. So another big factor, I think we touched on this before, is not only does the radar beam go higher in the sky, the further away from the radar site, the beam itself is also widening. Similar to the ham radio operations. So what happens here, 60 miles out, the diameter of the radar beam is already 1 mile across. 120 miles out, 2 miles, et cetera, et cetera. 240 miles out, we're looking 4 miles across. I mean, how many tornadoes extend that wide? In fact, if you think about it, 60 miles out, it's 1 mile wide. How many tornadoes are 1 mile wide around here? I mean, very much, almost never, right? So what that means is we're going to have a tornado. Maybe I don't have I guess I don't have the picture of it. So you can have a tornado that might be 1/4 of a mile wide, and the radar resolution doesn't pick up on it because all it sees is this wide, and so it averages out the wind from here to here. So it'd be like this. If we're looking here in the room, and let's just say people in the room here vary from 4'8" to 6'5". It's got all these numbers. It doesn't know that there's some 4'8" people and some 6'5" people in here. All it can see is that it looks like there's about a 5'8" people in the room. That's all it knows. It doesn't know any more resolution than that. So here's an example from my radar site. I just drew a little white wedge as it was going further and further away to the northwest, to give an idea of how large these little pixels are. In fact, if you're looking, depending on what kind of web page you're looking at or cell phone application, sometimes the radar will look very pixely. Other radar sites kind of smooth it out to make it look pretty and whatnot. But the hardcore data is basically these little boxy looking things like this, and the boxes get bigger and bigger the further away you go because the beam width is getting larger and larger the further away you're going. So here's the example of two different radars looking at the exact same, let's just say this is a big blob of rain or a big blob of hail in the middle of the storm. Two different radars are going to see something totally different. This radar on the right, it's filling up the entire radar beam. So it says, okay, yeah, I can see it's a good solid 60 dBz echo. The radar on the left, looking at the storm from much further away, like I said, it's a much wider, it only sees 60 dBz. It doesn't even see the 60 dBz. It's taking, all it does is takes the average of the overall picture and gives us that number. So when a tornado's on the ground for just a minute or two, with a 4 to 5 minute radar scan, we're liable to miss the radar altogether. The radar's not going to pick up a signature at all. So irregardless of the elevation, irregardless of the beam width, sometimes the storms just drop down to the tornado and they're gone within a couple minutes, and the radar has totally missed it altogether anyhow because it was tilted at 19.5 degrees when that thing touched down the ground. Another big one, you guys understand this from your all's hobbies as well. The radar beam does the same thing, super, sub, and standard refraction. We, in the weather business, and this is a terrible thing to say, I suppose, but we assume at all times that it's standard refraction. The reality is it's not, but you gotta, there's no way, at least we don't have a way of measuring. Today it's like 0.97 of the normal refraction. Today it's a 1.3 of the normal refraction. So with that being said, sometimes we're looking at storms and we think we're looking at a storm at 5,000 feet. Reality is we may be looking at a storm at 12,000 feet, or we may be looking at a storm at 2,000 feet. But all we know is that the normal refraction for this far away from the radar is typically, X number of feet up in the sky. There's a lot of issues associated with radars depending on what's located locally. So like for the Lake Charles radar, here, this is a picture of the rain totals for an event. And so a couple different features on here. You notice there's a funny looking wedge to the pointing to the southeast, where it should be all solid red through here, and it's got some lighter shades of yellows and oranges. That's because of a cell tower just to our southeast that is blocked as we're looking into portions of Vermilion Parish. And then going up here to the north, same thing. There's a wedge to our north. That's because of Burton Coliseum just to our northeast. That blocks us as we're looking up towards Fort Polk. So a couple of, and that's just us. I mean, different radars across the country have different issues where these are located. So we're going through all these different radar limitations. Now we've tilted the radar up at 6 degrees. You get this really cool feature. It looks like a ring. What we're actually looking at here is the freezing level, because the reflectivity or the precipitation that we're looking at here is all the same, basically the same shade all the way across at a certain elevation. We know from the meteorology standpoint that if we move our cursor over that band, if it's 12,000 feet or whatever, that's the elevation of what the freezing level is for that particular day. But from someone that has a nice radar app and they can look at all the different elevations and they see these funny looking rings out there, they may not know what they're looking at, but that's what these rings that you're looking at when you tilt the elevation. You're looking at just the one elevation, you're looking at just the freezing level at it.